So, good afternoon, everybody. Welcome to the second session of our second day. Let us welcome our speaker, Professor Shondeep Sen from Ashoka University. He is a senior scientist, computer scientist, whose research area includes algorithms and theoretical computer science, especially randomized algorithms, dynamic graph algorithms, geometric algorithms, and approximation memory hierarchy models, where several of his algorithms are among the best known in literature for corresponding problems. So, let us welcome him.
So I think I will be using my cordless. Does it have to be switched on or should it switch it off? Okay, yeah. Okay. So am I audible? Okay, so I would like to thank the organizers, the organizing team, led by Professor Arindam Khan, for really a very thoughtful program for the workshop. And I would apologize a little bit because I couldn't make up my mind for a while because of several other commitments I had this week. So only like last weekend, I was sure that I can make it. So my talk is prepared in a little bit of a hurry. Also, it's on a topic I'm not sure would be considered the most suited for frontiers of geometric algorithms. But then this is a problem that kind of started it all back in the 70s. When Graham, we all read about convolutional algorithms almost as the first algorithm taught in a course on either computational geometry or geometric algorithms. But it started it all, and then it remained, sort of an active, problem of interest for various reasons, not just because it is difficult to solve, because the first paper itself, Graham's paper, solved the problem fairly satisfactorily. But then it just, showed different dimensions, as people started looking at it, more deeply and tried to understand the complexity. So that's, it's like a little bit of a storytelling narrative that I will do, not so much of what is happening in the last few years, but there are significant results that came up, in the last 10 years. And this is like almost more than 4 to 5 decades of research. So let's take you through that. This is, as I said, looks like a toy problem, kids problem, but and many of you will be aware of many of the things that we're talking about, but hopefully there are things that you'll still be able to take away. Okay, let's move on. Just that, and this is just planar convex hull, it's not even high dimensional convex hulls. So planar convex hull, that's basically a set of points, and that's the smallest convex set containing those points. And as I said, Ron Graham back in 1972 proposed an algorithm that basically was worst case optimal. It's an n log n algorithm. So what is there to be done after 72? But then, as I said, it kept people interested, and there are some twists and turns. And this just, for completeness, Graham's algorithm basically just sorted the points in some polar angle around a point inside the convex hull, and simply did a kind of what we can call it like an angular sweep, to turn this simple polygon into a convex polygon. Right? This is where it was published in IPL. No, not in IPL. This was I think in it was IPL. It was IPL. Sorry, this is IPL. And just for remark at the bottom, the angular sweep was, the way it is exposed now, is the angular sweep has been replaced with, mode of line sweep kind of, so we don't have to explicitly work with angles. And also another comment that, the way Graham's algorithm worked, the Graham sweep, once you sorted the points, then actually it was just linear time. So it all came down to basically how fast you could sort. And sorting is another problem that kept the early algorithm designers busy for many decades. There's so many facets of sorting, so many interesting twists and turns, so many different models. And this is precisely the role that I think the planar convex hull has played in the area of geometric algorithms. Just to relate it to another very important problem, which is the intersection of half planes. And using suitable dual transforms, these problems are almost identical. So if I can solve one, I can solve the other. So this is just to impress on people who may not have seen it that the half-plane intersection can be solved within the same problems. And as I mentioned that no angle computation is required. You can just do a determinant sign, 3 by 3 determinant sign, which is nothing but the left turn, right turn kind of primitive. So we're not dividing, we don't need lots of precision. It's just, I think, polynomial of degree 2. And there were also, on the lower bound side of things, in the the algebraic decision model, in fact, even in the stronger arithmetic computation model, I forgot to mention here, there is this algebraic lower bounds of n log n, which goes much beyond comparison model because this is a truly two-dimensional problem. You require something which just beyond two. So they showed that even if you have the whole gamut of arithmetic operations available, still it is the complexity can be n log n. So essentially, Graham had the optimal algorithm, worst case optimal, right on day one. 50 years back. There is another version of the convex hull which just to sort of, because there is this close relation to sorting, and I said if you can sort, you're practically done because after that it's just linear time. People looked at another variation where so that you can decouple it from sorting, which is basically to answer the question, are all points on the convex hull? So for that, sorting is not required. Otherwise, sorting could be reduced to convex hulls. So even for this version of the problem, these lower bound techniques showed that it is n log n. So it's truly and firmly n log n. Okay, so after that, there were still, as I said, people were still looking at other variations and different ways of computing the convex hull. So a very natural thing is this gift wrapping thing. It goes under the name of Jarvis's march, where you're simply sort of tying a string around the points and sort of going around. And if you do that, do the analysis, clearly it's if there are h corner points in the hull, then it takes about h times n time. Okay. And now the question was that Graham had this n log n algorithm, which was also optimal. You have Jarvis's march kind of approaches where gift wrapping approaches takes n times h, and at least for some interval of h, the nh would behave better, right, for small values of h. So how do you reconcile this? This is a conundrum, and yeah, that kept people busy. And you, of course, can say that I can dovetail them or something and get the best of both, but then that's not a clean solution, right? So one needed to look beyond that. And also, there are a number of algorithms that emerged to establish this very close connection with sorting. So this algorithm design paradigms, I'm talking about basically late 70s, 80s, early 80s, where, you look at different ways of sorting, so you look at different ways to compute convex hull. So there is a counterpart for every sorting algorithm, like merge sort has merge hull, then insert hull, like insertion sort, and then you have this quick hull, to somehow mimic the quick sort. Okay, so quick hull, I will talk about it a bit more later, but let me first try to address these the hn versus n log n disparity. So this paper, which was published in, I think this is the first sausage, if I'm not wrong, 83?
It's not a sausage.
Okay,
it's
but
an Allerton conference.
It's an Allerton conference, yes. But I don't know. When I picked up, it showed sausage. 83.
Sausage started in 1985.
Yeah, that's what I thought. So somewhere, I got a wrong reference from this. Sorry about that. So this published this paper. The journal version came out in SciComm, but the conference version, something, that showed it wrongly to me. So it showed that this bound of n log h, the n log h bound, where the number of points is not even known a priori. Okay. Even in the Jarvis's march, h does not have to be known a priori. So, but then this bound clearly sort of closes that gap completely, right? So whatever be the value of h, and if you just go back, the n log n versus nh, if it is n log h, okay, then n log h can never be worse than n log n, okay? So that basically settle that part. And the most catchy thing about this paper was the title. And when I look back on it, so I think I and Pankaj were both doing our first geometry course in Santa Barbara. And so this was, at that time, a really hot result, right? That it is really can be done in n log h time, and this title of the ultimate planar convex Hull algorithm, like a rhetoric, can anyone really do better?
And the name of the technique was also provocative, marriage before conquest.
Yeah, right. Precisely, the marriage before conquest. Thanks for reminding me. Okay, so I mean, just in a nutshell, just to give you an idea of what this did. Again, to make the explanation easier. So when we are, thinking about convexual algorithms, we can basically do this thing that we can treat the part that lies above the line containing the leftmost and the rightmost point is the upper hull, and this is the lower hull. So you can focus just on the upper hull. So much of the complications, if at all, in the Graham's algorithm goes away if you do this. So we'll be basically talking about either the upper hull or the lower hull. These are symmetric problems. So if you look at Kirkpatrick's the Kirkpatrick-Seidel algorithm, what it did was it identified one edge of the convex hull, and then suppose this was this line L, then it could eliminate all the points within this quadrilateral. That's not very important. Maybe it could be empty also. The important part was that you will have to recurse on these left and right yellow regions, right? And then you could write this recurrence of the convex hull of n points with h corner points, and h is not even known. Then you could simply just write a recurrence of this sort, that the left part will have n1 points and h1 corner points, n2 points and h2 points in the right part. And the price for this was to find this edge. They solved a version of some LP problem, two-dimensional LP problem, and the real critical part of this recurrence was to show that both the halves of both the sides basically was less than some constant fraction of n. I just picked a 0.9, it could be anything else also. I think maybe they had a 3/4 or something. And that basically lends itself to the solution, that it is n log h. So it kind of magically falls out from that recurrence. And there are not that many, two-dimensional recurrence sort of in those days. So it all sort of came together, and it was considered, quite an achievement. So I said the partitioning used a two-dimensional LP, which was also something in those days. I'm talking about early 80s, which was a feat. Was somewhat complex, but on the other hand, what this started was a new paradigm of algorithm design, which is the output sensitive one. So I think it formally sort of brought in that, and that inspired so many other results, particularly in geometry, not so much in other areas. One of the most important in those days used to be this problem of hidden surface elimination, right? So where what is visible on the screen is essentially the projection, and you should be able to compute that scene in time proportional to what is visible and not what is occluded. Okay? Of course, there are all these hardware solutions on Z buffer and this and that, but so formally I would say it kind of ushered in the output sensitive algorithms. So that was one of the contributions of this paper.
Excuse me?
Yes.
Yeah, so you mentioned 2D LP, right? So what does it mean?
The 2D? Well,
Yeah, two-dimensional LP.
The LP with two variables.
Okay.
LP two variables. So they use this LP to basically achieve this bound. That they set up the LP in a way that the solution would basically, that there was a solution, and the solution would split the problem in a way so that it's not too skewed. And that if it is skewed, then you won't get that solution. Okay, it will be n log n. Yeah.
Is there also constraint on H1 and H2?
No constraint on H1.
But then how is there?
Well, I mean, so you just have to, yeah. When you see it for the first time, and clearly you are, you'll have to go back and just work it out. So it's by induction it works out. Yeah.
Suppose all the edge go to the side.
Yeah,
larger
that's fine.
Side.
That's fine too. So it's not at all. This is not an obvious solution at all. But let me assure you, it works out. Yeah. Okay, so the other part of story is the quick hull part. Okay, so again, I said there's a little bit of obsession amongst some people that we should get something that looks like Quicksort. Quicksort is a very successful algorithm, and so I have not been exhaustive in terms of references here. There are just too many, but some of them, I've just mentioned Eddy, Bikart, they basically tried designing a quick sort kind of algorithm, okay? And because, as I said, sorting and convex cells are very closely related, close cousins. And what is quick sort? Essentially, it's a partitioning algorithm. It's a randomized partitioning algorithm. So you wanted a similar partitioning algorithm, okay, for simple partitioning algorithm for the convex cell. And the initial attempts were basically that, okay, I mean, we are looking at only upper hulls. So you have this set of points, and any direction basically. Let's say, so we are going in the upper direction. So we find the extreme point in the upper direction, and then I can eliminate all the points within the triangle because they won't be in the convex hull. And then I recurse on the left half and the right half. Very similar to the Kirkpatrick-Seidel kind of thing. So these things were happening simultaneously. Except that, you could very easily conceive a situation where all the points will be on one of the sides, and then it will lead to that n square kind of behavior that you all are scared of, right? I mean, that's how quick sort is also sometimes criticized, that in the worst it is n square, although I don't believe that is a valid statement. The randomized algorithm is very much worst case n log n. But anyway, that's a different matter. So here, it's a completely deterministic algorithm, and certainly we can have situations where the points can be very skewed and will lead to that n square kind of behavior. Okay, so people didn't give up, and then this was happening probably more like in the early to mid 90s. Okay, so I have moved from 72 to about 20 years. So the idea was that, as I've only mentioned a few, I think there were three or four papers that were able to succeed, in a quick sort kind of algorithm. And the idea was that I pair up the points arbitrarily, okay, and do something so that I can eliminate a large fraction of the points, and when I go into the recursive mode, they are more or less evenly distributed, okay. So let me just focus on one such idea, and the idea was that, like quick hull, you choose a random pair basically, okay. You choose a random pair to choose which direction you want to basically find the edge on, okay. So here is the direction, and this is the edge corresponding to the direction, okay. And then you can argue, I'm not going to go into the details, that within that triangle, of course all the points disappear, but outside the triangle, you can argue that in a situation like this, when this is the pair of points, this point is going to go away because of the certain behavior of the slope of this line defined by these 2 points compared to this line L, which was a kind of a random direction. It's not a completely random direction. See, the randomness is not coming from a random choice of angle. The random direction is coming from a random pair. So it's a random direction among those n over 2 pairs. Okay? So that's very critical. Only then basically it's happening. So you do this, so you can discard one of the points, and then essentially you can write now a probabilistic recurrence, okay, where same thing, the same recurrence as the Kirkpatrick-Seidel, but now because you're choosing random direction, I can argue that again you're going to discard there will be not more than about some fraction of n points on one side, which will give you this solution. Yeah, you had a question? No, it's up here. Um, and it can be actually the algorithm can be improve. I mean, you can prove concentration bounds for larger values of h. So you could do something almost like quicksort. And if you can make this algorithm complete deterministic also, and that's basically what what can happen in quicksort also, right? If you choose the splitter deterministically using a deterministic median finding algorithm, it becomes a completely deterministic algorithm, which is same thing in n log n behavior. Worst case, and it used to be an n log h worst case behavior. Okay. So the reason I'm saying double delight is it is not only very simple, okay, at least the version that I showed you, it is extremely quicksort-like. I'm just pairing points and choosing a random direction. The pairing points is not even required. It's just arbitrary. I can choose whatever the sequence of points are given to me. So the only thing I'm doing is again choosing a random direction and choosing this edge. So if you choose it, the median, it actually gives the guaranteed n log h, deterministic n log h bound. But if you do it like exactly the quicksort, choose a random direction, you get somewhat better constants. Okay, so this basically, I think, settled the quicksort versus quick hull part. Okay. So let's move ahead. What next? How much time do I have? Is that the clock that I should follow? 10 minutes? 15 minutes? I'm towards, I mean, I don't need too much time. Just checking.
5 minutes.
Oh, okay. Let's see. That's the bargaining thing. All right. So, okay, so here I've just drawn
We
something.
have actually a lot of time. We have 45. So
Oh, well, okay. I won't need it. So we can have a discussion. I can repeat the talk. All right. So here you are with. I'm just showing that look at the upper hull, and the upper hull I'm looking at these parallel slabs divided by the upper hull, and there are these points in each of these vertical slabs. And I'm just, sorry, I did not use the subscripts, basically n1 points, n2 points, n3 points. So there is kind of a vector, suppose there are h points, so there will be a vector which is the points under the ith slab. Okay. Of course, this vector is not known to us. We don't have any idea about h, neither about this vector. Okay. So there is this, just a very simple trick, okay, where the analysis is done in such a way that the algorithm now has a bound like this. Now this expression, if you have not seen before, I'll let you stare at it for a minute or so. So recall that nth of I is the number of points in the ith vertical slab. Of course, it could be 0 if all the points are on the hull. But whatever it is some. If there are h points, ni is the number of points in the vertical slab. And there is this expression which would remind you of basically something you have seen before, very entropic like. And we have no prior knowledge of this. And this expression, okay, is always bounded by, okay, sorry, I have used k here, it should have been h. It's always going to be bounded by n log h, which is the bound that we are looking for. And actually asymptotically better than in many situations where these ni's are very skewed. So for instance, I'll give an example where one of them is very large, the other about root n, and then n log h will be n log n because there are root n points in the output. But this expression is bounded by linear. Okay, so this expression is no worse and in many situations better. Okay. So let me switch, to explain this, I have taken the example of the maximal problem, which is the easier problem to talk about. So hopefully everyone is familiar with this, that there is the staircase basically, and we're trying to find all the points that are not dominated. And I could do the same thing, that under each of the slab I have ni points, n1 points, n2 points, etc. So these problems are also very related. It was the convex null in the L1 metric and this too. But it's easier for me to explain. So that's the reason I chose this. So an identical bound can be proved for this. How is it proved? Okay, so this is the reason I sort of use this to explain it. What you do is you find the staircase step over the median. Okay, and whatever is the median, okay, the points under that step will all disappear because there can't be maximal points. Okay, and then you recursively go on to the left side and the right side. Okay, so when you do that, just this part, okay, you just use a charging argument based on how many times can a point enter recursion. So in the first time, the step that was the median step, all the points underneath will disappear. Other points will survive, but then at some point, because we're doing the same thing recursively, it's going to be sandwiched, and at some point it's going to disappear. Okay, so how many times will it survive the recursion? And that's basically nothing but this expression n over ni, log of n over ni. That's it. So that's the analysis. Sorry, and that gives you that bound. Okay. Sorry, I'm being a little terse, but what I'm saying is that just this part, that it is shrinking by a factor of 2, you can just plug this in, that any point, say the point under the ith slab can only survive for log of n over ni, and there are ni points, so that's the summation. Okay. And this expression, I said, is upper bounded by n log h. So the n log h bound can actually come for here. You don't have to do anything more, and it's even better. And there is a corresponding lower bound, so it goes back to a paper that I co-authored in the late 90s. And I've been I was initially excited, but then I could not extend it beyond this basic geometric problem. So I thought initially that this paradigm could be interesting for many other problems. And that's one of the reasons that I thought that maybe I can bring it to the notice of this audience and they can think about other things. Okay. So we had the lower bound was that expression, which means that we beat the lower bound of n log h. Okay, and that happens because the n log h, for the n log h bound, the points have to be in a certain worst case, combinatorial distribution, which will give the n log h. But then, without changing anything, just by viewing the problem as these vertical slabs, my lower bound changes, and actually it's a sharper lower bound. Okay. So the question is, why did we get it? How did we get it? So as I mentioned before that this expression is very similar to an entropic expression. Okay. So can you do anything more with it? And that's something that I really did not succeed much. I could do it for the convex hull, planar hull. I could do it for the two-dimensional maximal, and probably it could be pushed to the few dimensions higher. But then what about other problems? Other problems from other domain, not just geometry, how about some graph problems?
So it's interesting that the entropy expression is coming even though the algorithm is completely deterministic.
It's completely deterministic, yeah. So I can make that algorithm deterministic also. Yeah, absolutely right. Yeah. And so, and the thing that bothered me was also this part that, the definition of this entropy was direction dependent, right? It's very vertical. So I defined the slabs vertically, and there's something not natural about it. I mean, particularly for a convex hull, which is rotation invariant, one should be able to get a better, sharper, more natural expression. That's something that happened down the line. This is a paper that I'm talking about that happened about 10 years ago. It's a JACM paper co-authored by Timothy Chan and his students, where they took this approach and built on this. They actually managed to define something called a structural entropy. So I didn't use the word entropy there. It was called distribution sensitive algorithm. So from output sensitive, I called it distribution sensitive algorithm. But they went ahead and actually, okay, I don't have it here. So this goes under the name of instance optimal algorithm. Okay, I'll come to that maybe in the later slide. I'm sorry?
Instance optimal geometric algorithms, that
I can't hear you very well.
Instance optimal geometric algorithms, that's one.
Instance optimal, yeah, right. I'll come to that. So they managed to basically show that instead of the vertical, so I'm again sticking to the two-dimensional maxima, it is easier to explain. You can actually do these partitions any way that you want, and you still get that bound. And this I also knew that whether it did it vertically or horizontally, it will be the min of that. So they basically just carried out that job and showed that they worked with basically boxes, axis parallel boxes, and showed that look at any box and those points are going to also disappear in the same rate that I mentioned in the vertical set. Doesn't matter how you pick those boxes. Okay. So this is the structural entropy, the same expression, okay, and they called this, a respectful partition, and they managed to prove a tight bound for the maximal problem. The convex hull, yeah, okay. So the lower bound used a kind of a KD. It goes like this guillotine cuts kind of things. You can bridge those boxes using the guillotine cuts. So they use some kind of argument based on KD trees to show that that bound actually is optimal, and they are looking at. I should have written it. The min over all possible partitions. So now, it's not just the vertical or the horizontal, but any partitioning that you choose, which they call the respectful partition, the structural entropy bound would hold. So you are going to look at the minimum entropy. So that settled it. Okay, I mean that made it more the bound more stronger. The extension to convex hulls was a little bit more complex because then you have to talk about some kind of simplicial partitioning. But not many new ideas were required, but it was definitely more laborious to prove that. So, but they took it through. They took it through to higher dimensions also, and so I want to basically summarize this part, which is more or less my last slide, saying that this kind of indicates or is indicative of another paradigm of algorithm design that goes beyond just output sensitivity and what I call distribution sensitive to what they called instance optimal. So this is basically the way you can pose the problem for a given the challenge. That's for a given problem P, can we design an algorithm such that for any instance, okay, that algorithm will be competitive with the best algorithm for that instance, no matter what this instance is, and you can choose the best possible algorithm for that instance. Okay? And if you really manage to do that, you have kind of almost found an alternative to the normal worst case bounds. It is worst case, but it is extremely powerful. That you're not saying that I have some instances which are very hard. My algorithm will be competitive only for the hard instances, but I may lose out for the simpler instances. So this paradigm says that whatever be the instance, I can match. This one algorithm will match the best algorithm for that instance. Of course, clearly, this definition is too strong because then, for a specific instance, I can hard code something. Especially, if you look at, things that depend on permutations. So, for a particular sorted permutation, convex hull will be easier, right? So then we need to sort of strengthen this notion, going to take care of the order obliviousness. That the algorithm that is going to address a particular instance, should not depend on the ordering. But whatever ordering I give for that instance, I shuffle that. Only those algorithms will be legitimate, for us to compare with. So clearly, sorting cannot fall in this class. But there are many algorithms that are the order oblivious. Most graph problems are order oblivious. All the hard problems in life are order oblivious. It doesn't matter even if you give the permutation, nothing happens really. I still struggle, right? So this is the story essentially. That convex hull has actually taught us in terms of many different algorithm design paradigms leading up to this, distribution sensitive or instance optimal. Again, I leave the audience with this question: that can this really be extended to problems of interest in other domains, where the idea is let me just be a little philosophical, that if you think about low dimensional computational geometry, in some sense, we were looking at what is now known as parameterized complexity. Okay, so you want to can separate out the terms depending on dimensions, and you get very good running time if the dimension is small. Okay, if the normal worst case way of designing algorithms is only looking at the input size, that is n. That's all we know. If you bring in the output sensitivity part of it, it's another parameter, it's an unknown parameter, but it is h. So it's basically a function of two parameters. You go to this distribution sensitive or instance optimal kind of design, I have a vector of parameters which I don't know about, but somehow I can analyze the running time in terms of those parameters, which subsumes all the previous kind of work, okay, and actually gives me a better or a more smoother behavior in terms of how it behaves from a certain kind of configuration to a worst case kind of configuration. So can we actually then think about parameterized complexity where it's not about one or two parameters, it's a whole family of parameters that could be dependent on the problem itself, and some insightful analysis of that algorithm could give us a performance that will show a smooth degradation from an easy instance to a hard instance. Okay. So I leave you with that, and thank you so much. I'm happy to take questions. Yeah.
So, you mentioned N log H is a lower bound also?
A lot
Is it
used to be low bound, but you are only considering n and h here.
So is it obvious how to show this?
The n log h bound?
Yeah, did you say?
The n log h bound, the initial lower bound was based on the algebraic decision tree model. It's not easy, I mean, it's not obvious, but it is an interesting extension of the Yao-Benor kind of bound. In fact, the reason why we know about it, I know about it so well, and Pankaj also, because the person who did it also taught us the course. So I think very easy.
So, any more questions?
So there are very sort of nice connections between entropy and counting problems.
Well, I mean, you would have seen that this is also the expression for multi-sorting,
Yes.
which is known from the Knud's volumes or even further.
So is it, but it's quite interesting that it's coming out more of the analysis than a counting.
Absolutely. Absolutely.
Okay.
And these kind of parameters are emerging kind of in an invisible way. I don't need to know about it. Whereas there are also n log h algorithms which tries to guess h. It's like standard doubling technique. If h is so much, then I do something, and then it kind of all sums up telescopically to the n log h. But that's something, it's fundamentally different from something where you're just working on something and it is kind of emerging, and the analysis will give you the expression.
And so again, just to go back to the fact that the vertical slab counting exercise, which you mentioned, like the was extended through these boxes things.
Right.
Have ideas of like actually like rotating the axes or
So when you look upon the maximal problem, it is axis parallel. We can't do much about it. But the convex hull, of course, is rotation invariant. So they also required, different. The boxes were replaced with triangles. That is called the simplicial partition. So you basically do it for simplices, and they could do it till about, I think, dimension 3 or something.
So I think you said you needed a certain proportion of the points on both sides.
Right.
So is that something which is, so I mean, you said 0.9, but it could also be.
Yeah, the closer it is to 0.5, the better in terms of constants. The n log it will have a leading constant.
Any more questions? So, let us thank Professor Shen again. Let us welcome our next speaker, Professor Esther Isra from Bar Ilan University. Her research interest includes computational and discrete geometry, geometric approximation algorithms, randomness in calculation, differences in geometry. Today, she is going to talk about new developments on intersection searching in 3 space.
Okay, so thank you very much for the introduction and for inviting me. So I'm going to talk about intersection searching in 3 space. So this is a central area in computational geometry and it's part of range searching. And I'm going to talk today about 3 specific problems which will demonstrate this area. So the first one, which we call line-amid unit ball intersection detection, is the following. B is the input. It consists of n unit balls in 3-dimensional space. And the goal is to pre-process them into an efficient data structure that supports line intersection queries. What does it mean? Given a line in 3 space, you would like to efficiently report all the balls that it intersects, if any, or just report whether the intersection is empty or not. This is the detection. And the dual question, which we call unit ball and midline, line intersection, is where we flip the roles between the balls and the lines. So now the input consists of lines in 3 space. And the goal is to pre-process this line into an efficient data structure that supports unit ball intersection queries. That is, given a unit ball, you would like to detect whether it intersects any of the lines. Okay, good. And problem number 3 is the so-called nearest neighbor searching. So here we are given a set of n lines in 3 space, as before. And for a point q in 3-dimensional space, the nearest neighbor q, the nearest neighbor of q in L is defined as the line that is closest to q, that it brings the distant function to a minimum. Okay, the closest line to q among L. So the nearest neighbor searching a midlines problem is to pre-process L into a data structure that supports efficient nearest neighbor queries. Okay? So apparently this question is also strongly related to intersection searching, and I will show the connection between them. Okay, so let us begin with the first problem, line amid unit balls intersection detection. And what I'm going to do now is to reformulate this question as a range searching problem. So in range searching questions, we are given semi-algebraic range searching, we are given a set of points in some d-dimensional space. The goal is to pre-process this point so that we can answer efficiently range queries questions. For example, given, say, a range which is a simplex or a ball or any other simple shape that you like, you would like to efficiently report the subset of the points that it contains, or count how many points does it contain, or answer whether it contains any of the points. This is the emptiness of detection. Okay, so in this question, since all the balls have the same radius, then we can obtain the following question. So we are going to look at the centers of these balls. This is a set P of points, this point. And now the question of line intersection becomes a unit cylinder range query. Because now the problem is to pre-process P into a data structure that supports unit cylinder range searching queries. That is, if the cylinder contains any of the points in the input, it means that in the original problem, the line intersected at least one ball. Okay? Range searching queries, we are going to focus on determining whether the intersection is empty. Like I said before, I'm highlighting it. So this is called so-called emptiness query, or to report the subset of the points that the cylinder contains. Okay, this is called range reporting. This is called range emptiness. Okay. So before I proceed with this problem, with this question, I would like to just give a quick review of the previous work. So this question belongs to the family of the so-called ray shooting or line or segment intersection searching. So this is the demonstration of three-dimensional ray shooting problem amid triangles in 3 dimensions. So here you can think about the line as a directed line, and you would like to report the first object, in this case the first triangle hit by the ray. Okay, by the way, the ray shooting is also related. It has applications in hidden surface removal, one of the questions that Sandeep mentioned in his talk before. Let me summarize a few of the known results, just a short list. So in 2 dimensions, when the input consists of segments and the queries are also segments, and we would like to detect intersections, we can construct a data structure of space query trade-off of m and n over m to the 1/2. And that in particular means that when the storage is quadratic, the query time is polylogarithmic. Okay, so this is a trade-off bound, and when the storage is roughly linear, the query time is root of n. And here, and what follows, O star hides a factor of the form n to the epsilon. Okay, and very recently in Sausage this year, Chan, and Zhang showed that for algebraic arcs, this answering segment intersection detection or ray shooting amid algebraic arcs can be done with space of roughly n to the 3/2 and query time of n to the 1/4.
So what is epsilon?
Epsilon, so the real epsilon is a factor of about 2 to the power of root of log n. Sometimes it hides only polylogarithmic factors, but this is the way we treat it.
But what's the role of epsilon? So maybe I missed.
Oh, so epsilon appears in the concept of proportionality. So you cannot have epsilon to be strictly 0, because then the concept of proportionality goes to infinity. But for any small epsilon, you get a bound. So the bound is n to the 2 plus epsilon. Okay? All right, so in 3 dimensions, Adoral and Matushak shows that we can answer ray shooting amid planes with storage and query trade-off bound of m and n over m to the 1/3. And for triangles in 3 dimensions, this is the trade-off bound. And that was the bound until recently. And then in 2021, Michael Shari and myself, we improved this bound to this amount of storage in root of n query time. So this also improved the trade-off bound. And we use the so-called polynomial partitioning technique. And for spheres, this is the case that we are going to focus in this talk. The trade-off bound is m and n over n to the 1/3. So this was given by two works with Mohaban and Sharir and Shaul. So in the first work, they show a bound of space and pre-processing bound of close to n cube, and the query time is close to constant. And in the work of Sharir and Shaul, they show this bound, a linear storage, and to the 2/3 query time. So once you have these two bounds, you can get this trade-off for any n between n and n cube. Okay. So this is more or less the state of the art, and now let me state our results. So for the first problem, we are given a set of unit balls in 3 dimensions. We show that we can pre-process B, the set of unit balls in times n again into a data structure of linear size, so that line intersection detection queries can be answered in mod of n time. And this improves the previous bound of Sharir and Shaul. They solved ray shooting, but in particular that includes line intersection detection. So for arbitrary ball, the bound was n to the 2/3. So this is the improvement. And as for the dual problem, where we are given a set of lines that we would like to answer unit ball intersection detection, we showed a nearly quadratic storage data structure with query time that is logarithmic.
So what is the preprocessing time of the arbitrary ball sets?
The first one?
SS result.
This one?
Yeah.
So the preprocessing time is proportional to the storage complexity, which is also linear. Okay, so usually in line searching, I mean, when we say storage, we have storage, query, and preprocessing, but storage and preprocessing come together, and they are asymptotically the same up to an n to the epsilon factor. Okay, so I'm going to focus on this problem, but before that, let me also state the result about the third question, nearest neighbor searching. So here we are given a set of lines in 3 dimensions, and we show that we can preprocess this set in time and space, which is very close to linear, such that nearest neighbor point queries are answered in n to the 2/3 time. And this improves the so-called startup bound of n to the 3/4. So this bound is just given by an appropriate parameterization to range searching. And in order to get this bound, we had to work much harder. So the connection between this question to intersection searching is through the so-called parametric search. So Agoral and Matushek showed that nearest neighbor searching can be reduced to the following intersection searching problem. In the sense that they are equivalent up to some logarithmic factor, polylogarithmic factor. So now I call this problem as problem 3 prime. And this problem is ball amid lines, intersection detection. So here we are given a set of lines as before, but we switch the nearest neighbor point query by a ball intersection detection query. That is, this is the decision problem where you would like only to detect whether a ball intersects any of the lines. Okay? So this is an intersection searching problem. Okay. One of our main tools is the partition trees of Matushek. So in the next few slides, I'm going to demonstrate this technique, and then I'll show how we apply it for our problem. So Matushek presented this technique for hard spaces in d-dimensional space. So this is for range searching amid points in this space and half spaces. Okay, so P is a set of endpoints in d-dimensional space, and R is the parameter of the partition tree. So we say that we define elementary cell partition for P as a collection of pairs, P1 sigma 1 through PM sigma M, where the number of these pairs is order of R. Again, R is the parameter of the partition. And P1 to PM, this is the partition of P into pairwise disjoint subsets. And each of these sigma I is what we call an elementary cell that contains PI. So elementary cell is any nice shaped cell like a simplex or prisms and so on. And so this is a demonstration, this is an illustration in 2 dimensions where the cells are simplices. And all the sets PI have more or less the same size, which is roughly n over R. What else do I want to say here? Yes, that the cells sigma I are not necessarily disjoint. So again, you can look at this illustration in 2-dimensional space. So this is a partition, but we need to have an additional crucial property which says how many cells are crossed by a given range. In this case, this is a half space. And it is illustrated by this line, which bounds the half plane in 2 dimensions. So Matuszek showed the following property about what is called the crossing order of the ranges, which in this case is a half space. So given a set of points in the dimensional space, R is the parameter of the partition, there is a simplicial partition, phi, such that each half space crosses at most that many cells in the partition, R to the 1 minus 1 over D. For example, in the plane, this is only root of R. So crosses means that it intersects, but it does not fully contain. Okay, as you can see here in this illustration. So once we have this property at hand, we can apply a recursive scheme and build what is called a partition tree, and eventually extract from that a data structure of linear size, which answers half space range queries in time close to n to the 1 minus 1 over d. Okay, so this is the situation for points and general half spaces. Now the question is, what is the situation where these half spaces contain relatively small number of sets? This is what some number of points. This is what we call shallow half spaces. Okay, so we have the same setting as before, P is set of points in dimensional space, R is the parameter of the partition, and now we are given a set of half spaces that are shallow, in the sense that each of them contains at most n over r points of P. So so the question is, should the crossing number improve given this information? So this is an illustration for a shallow half space, and this is a not shallow half space, and this is the direction of them. So the answer is yes, we can improve it. And this is another theorem shown by Matuszek. So given a set P of points in the dimensional space, we have to admit a simplicial partition such that the crossing number for all the shallow half spaces is this bound. So as you can see, this is an improvement with respect to the previous general bound. And again, once we are given this property, we can derive a recursive equation and obtain a simplicial partition tree, which eventually results in a data structure of linear size and query time, which is n to the 1 minus 1 over d over 2. Okay? So, and another important property about these partitions is how to get such partitions. So one of the crucial properties that we are also using in our analysis is to build what is called a small test set. So a test set is a set that well represents all the ranges. In this case, these are half spaces. So you would like to have a small set of half spaces that admit a small crossing number. And once we have that, we'll be able to claim that all half spaces, or all shallow half spaces in our case, will also have a small crossing number. And therefore, we'll be able to derive such a nice data structure for them. So, the test set lemma of Matuszek implies the following. He showed that there exists a test set Q of that size, R to the D over 2. Now the parameter R is usually taken much smaller than n, close to a constant. So this is indeed a small set of ranges. So there exists a set Q of that many shallow half spaces, so that for any simplicial partition pi, the following holds. So if kappa is the largest crossing number of the half spaces in Q, then any other n over r shallow half space crosses at most order of kappa. Okay, so they admit the crossing number up to a constant factor. Okay, so that was a short sketch about simplicial partitions and the work of Matushek. And now let us return to our work. So we have more general ranges in the question about points and cylindrical range queries. So we would like to build similar data structure. The problem is that it is much more difficult to construct a small test set in this case because the properties that I showed before strongly rely on the fact that we have half spaces, and these are linear ranges. And in this case, they are not. So, long story short, it all breaks down. It doesn't work. So we will need to use another skill. So in general, in order to, the properties that we need to have is to find a small test set Q. We need to construct it efficiently. And of course, we need Q to represent all the shallow ranges. In our case, these are shallow cylinders. And there is also another crucial property that the complexity of the union of the ranges of Q is small. Let me explain. Let me read first and then explain. And furthermore, we also require that the complexity of the decomposition of the complement of the union is small. So let us look at the case of half spaces. This is a two-dimensional illustration. So these are actually half planes. So the union of half planes, the boundary of the union is actually the boundary of a convex polygon, right? So this is the complement of the union. This is the area that lies, so to speak, above the upper envelope of all these lines. So, so for half spaces, the complexity is small, so to speak. This is the complexity of a convex polyhedron, the intersection of half spaces. And furthermore, we also have a good decomposition for this complement. So here, I only sketch what is in 2 dimensions, what is called the vertical decomposition, where we erect vertical ray to y equals plus infinity. In general, for half spaces, we use what is called the bottom vertex triangulation. But the bottom line is that there are good decomposition in the sense that the complexity of the entire decomposition is proportional to the complexity of the structure, which in this case is the complement of the union. So such properties hold for half spaces, but for general algebraic ranges, this does not necessarily hold. So this is what we were fighting with. How much time do you have? How many?
20 minutes.
20. Oh, great. Wonderful. Okay. So let us return to the problem, just like a reminder. So P is a set of endpoints in 3-dimensional space. These are the centers of the ball. And we would like to preprocess them into a data structure that supports unit cylinder range emptiness queries. So what we are aiming for is to build such a partition, an elementary cell partition for the points in P, such that any shallow unit cylinder will cross only roughly root of R cells. So once we have such a property, again, if we apply recursion, we will be able to build a linear size data structure with a query time close to root of n, which is the result, the promised result, okay? So we managed eventually to show such a property, but that requires some work and some canonization. So let me tell you a little bit about it, how we build small test set. So here, for general ranges, general objects, there is a technique to build small test set. So we follow the recipe of Sharir and Shaul. So one of the things, the properties there is that the objects in the test set are no longer equivalent to the original objects, as in the case of half spaces. In the case of half spaces, we had the queries were half spaces, and the test set was also consist of half spaces. Here, the test set does not consist of unit cylinders. They are what we call generalized cylinders. So here is an illustration. They look like a swept volume of unit cylinders. And this follows by the recipe of Sharir and Shaul. And they showed that one can build such test set, and it satisfies the properties that its size is small, it's only polynomial in R, and R is small. It is shallow in the sense that its general cylinder contains only n over R points. And every shallow cylinder from the query is contained in a single element of Q. So this set also well represents all the queries. The catch is that what we need to show is that the complexity of the union of these objects is small. And this is in order to fit this property in the partition tree technique and obtain the desired data structure. So this is the main thing that needs to be shown. So let me tell you a little bit about union of objects, just to get a sense of it and getting into the mood without getting into details, of course. So generally speaking, the complexity of the union of objects in three-dimensional space is cubic in the worst case. And this is the example. The example is a grid. So just think about infinitesimally thin plates.
So is it for any 3D object or?
The 3D object of constant complexity. So nice objects like simplices, balls, ellipses, any objects of constant that are defined by constant degree polynomials. Okay, so here, I mean, a three-dimensional grid, it has n-cube holes, and so definitely the complexity of the union, the complement of the union consists of at least n-cube holes, and therefore it is n-cube. So what we showed, or what we need to show in our case, in order to guarantee the root of n query bound, is that the union complexity of the general cylinder is only quadratic. It is smaller by one order of magnitude. So in general, it doesn't hold, but what we managed to show is that it is sufficient to obtain such a bound for a union of general cylinder within a very small slab. Okay, and then what we did here, without getting into the details, we made a reduction to what is called lower envelope in three-dimensional space. So the lower envelope of monotone surfaces is the scene that a reviewer sees when she looks upward. Okay, so this is, you can also project them to a lower dimensional space and get the so-called minimization diagram. So they are known to have nice properties, and one of them is that the complexity of lower envelope is only quadratic. So once we made this reduction, we got the property that the union complexity within a small step is only quadratic. Okay, but this is not enough just to show union complexity. We also need to have an efficient decomposition of the complement of the union. So this is an illustration of the composition of a lower envelope in 2 dimensions, lower envelope of algebraic curves. So the lower envelope is again, is this line. So again, this is the scene that a reviewer sees when she looks upward. And the composition is fairly simple, right? You just decompose them into vertical prisms that are infinite in the minus y direction. And so in 2 dimension it's easy, but in 3 dimension this is getting way more difficult. And such decomposition for the complement of the union is not known. So just in terms of the chronological order of the events, in the work with Pankaj in 2023, we didn't have such a decomposition. And so what we did, we bypassed this issue. We applied some canonization and we make reduction to lower envelope or vertical decomposition of lower envelopes, and we obtain this result. But then a year later, together with Mr. Sharir, we actually managed to show that such an efficient decomposition exists. So again, when I said efficient decomposition, I mean that we can decompose the complement of the union into simple shaped cells, such as prisms or simplexes, such that their overall complexity is proportional to the complexity of the structure, which is the union in this case. Okay, so eventually we managed to show it. So it was not that necessary for that work, but it is necessary for the third result about near-stable search. This result, okay? So, so a reminder, in the near-stable searching problem, we are given a set L of lines in three-dimensional space, and we would like to process it in order to efficiently support nearest neighbor queries. And we reduce this problem to the problem of intersection detection of balls amid lines. Okay, this problem. So, in order to solve this question, what we need to do is to characterize this question as a range searching question in four-dimensional space. Okay, so we proceed as follows. So lines in free space are defined by four parameters. For example, one of the ways to do it is to take a line and the two planes, parallel planes z equals 0, z equals 1. From each of them, we collect the two x and the y coordinates, and we get four parameters. So roughly speaking, a line L can be mapped to a point L star in four-dimensional space. And balls, we are going to map them to monotone surfaces in four-dimensional space, such that in the primal space, a line intersects a ball if and only if the appropriate surface will contain above it a point in the parametric space. Okay, so after some canonization, a ball sigma in three-dimensional space can be mapped to a monotone surface, which I call gamma sigma, which consists of all, it represents all the points L star, which represent lines that are tangent to sigma from below, as you can see in this picture. Okay, so this is an algebraic surface. As a matter of fact, it is a monotone surface after appropriate canonization. And then sphere intersection query becomes what we call semi-algebraic range emptiness query. Like I said, the line intersects the ball if and only if the region above gamma sigma contains the point L star. So this is the problem that we want to solve. This is a semi-algebraic range search in four-dimensional space. So roughly speaking, we can solve such questions in data structure of linear storage and n to the 3/3, 3/4 query time, but we improve it to n to the 2/3. Okay, so here too, the main challenge is to construct a small test set. So we follow the same recipe of Sharir and Shaul, but now the question is, of course, how the test set looks like. So in this case, the objects in the test set, we show that they are generalized monotone surfaces in four-dimensional space, and they are obtained by a continuous motion of the surfaces gamma sigma that represent the ball. So, so in this case, the union or the complement of the union of this monotone surfaces is, as a matter of fact, is the lower envelope of surfaces in R4, also known as graph of trivial functions. So this is what we are getting here, and this is a three-dimensional illustration. Oh, this is not working. Okay. So what we need to do, we need to show that the complexity of the lower envelope in four-dimensional space is cubic, and that we can decompose it into a relatively small number of cells. So the first property was already shown by Sharir many years ago, And this shows that the complexity of the lower envelope of n-trivial functions of constant complexity is only n cubed. But again, this is not enough. What we need to have is an efficient decomposition of such lower envelopes. And that was one of the contributions in the work from this year. So we showed that the complexity of the composition of the lower envelope of F, we use vertical decomposition, but I did not define it specifically. We showed that there is such a good decomposition whose overall complexity is n cubed. And once we have, okay, so this is a big hammer. But once we have this property, we can just plug it into the machinery of Sharir and Shaul and get the desired data structure for nearest neighbor search. For intersection searching and therefore for nearest neighbor search. So that's it, that's my talk. Thank you for listening.
Are there problems in 2 dimensions of this clearer which are interesting?
Again?
Are there problems in 2 dimensions which are interesting? This
So in 2 dimensions, most of the problems, so solving intersection search in 2 dimensions, like I stated, the follow-up work is already known. So last source at Chan, and then show a data structure of size into the 3 halves with query time of into the 1/4. So again, not that we ran out of all the problems in 2-dimensional space, but many of them are already known. Yes. In 3 dimensions it is challenging. In 4 dimensions we have no idea because getting the composition in higher dimension is even way more challenging.
For constant description complexity objects in higher dimensions, so these techniques that you have for showing the union complexity quadratic is it possible to generalize?
So it becomes much more difficult. What we know about high dimension is the complexity of the lower envelopes. So lower envelopes in any dimension D, as long as the degree is constant, is roughly into the D-1. But yes, union complexity, once the objects are not monotone, it becomes really problematic. So unless you find a canonization, a right decomposition in order to show that you can reduce it to monotone objects like lower envelopes, yeah, so that's a pain, I have to admit, yes.